Okay. So today we will continue with what we were doing. That is finishing the understanding of Gaussian beam, which is basically uh, very crucial in the sense that all laser beams that you encounter. I mean, okay. I mean, should not say all possible laser. Yeah. I mean, uh, unless a laser goes bad, the transverse intensity profile is almost always Gaussian. There are some extremely specialized lasers which actually give you higher order beams as well, but those are not something that you are generally dealing with, and those are very, very, very rare where you get higher order Gaussian beams as the principal output. What we are dealing with is the fundamental Gaussian, and that is extremely important a beam mode. So that is the most simplest of all beams. And of course, we know that plane waves are not beams. So the a beam is essentially something whose some light where the transverse extent is confined, and the Gaussian gives the fundamental. So what we are dealing with are actually a class of solutions of and these are all they are part of this broad family of Hermite Gaussian series of solutions of the Helmholtz equation, which the basic boundary condition of which, of course, is that the longitudinally, that is the direction of propagation of the beam, the variation of the intensity or the yeah, is much lesser compared to the transverse extent, where the beam basically uh, falls off in the intensity, falls off very sharply, and that basically provides some kind of boundary conditions to the Helmholtz equation, so that the in the z direction we ignored the double derivative, and that gives rise to a class of solutions whose fundamental or ground state is what we are considering now. Of course, the way we have dealt with the solution is that we have just said that these are just we have taken the fundamental Gaussian mode as uh, the sort of the possible solution towards this. So a more general thing is, of course, the entire Hermite class of polynomials. So we will actually study some of the more exotic beam modes, the Hermite Gaussian beam modes, as they say, after we finish off the fundamental Gaussian. However, the fundamental Gaussian is what is most important, because that is what you have in lasers. And not only that, it is also very important to study just not the beam itself, but how a beam, that is the Gaussian, that how that interacts with a resonator. So you remember that before we touched upon this, we actually studied when a resonator which is basically nothing but a Fabry-Perot cavity, two mirrors which face each other, and which causes a beam to sort of reflect upon itself. But then it also there are some conditions which kind of dictate whether the beam or so will we actually study just how a ray propagates inside the cavity or the resonator, and we have by this interaction, by this type of the ABCD matrices, which essentially describe how a ray interacts with a piece of optic, which is a mirror, curved, uh, uh, or even plane, and lenses. Typically, convex lenses are what really we use mostly in the lab. So how these interact with light rays is what we have studied. However, reality is not rays, reality is beams. So the finally, the what we shall deal with is how a Gaussian beam interacts with a resonator, how the stability conditions, how they are interpreted in the beam picture that we have now. This, remember that this beam picture is much closer to, is indeed what reality is. And this is very critical because a resonator finally lies at the heart of any laser. Okay, so light amplification, which are the first two terms of the acronym called laser, that happens basically because of interaction of this light, which is emanated as fluorescence, interaction with a fabry cavity, and therefore it is contingent that we know how a Gaussian beam, the ABCD law for Gaussian beams. That is what we're going to touch upon today, and finally the resonator physics in terms when the incident when the input beam into the resonator is actually a Gaussian. It's actually a beam. So we just studied rays. We are now going to study beams. Okay. So before we study the ABCD law, let us just start. We'll just end the basic discussion on Gaussian beams by calculating first the uh, the total energy that is important. So we have written down the electric field. So what we studied last class was that the fundamental Gaussian mode of the Gaussian beam, there are two things we studied. First is that the propagation of the Gaussian absolutely emulates the diffraction of a plane wave through a circular aperture, in the sense that the radial spread or the waist size of the beam is actually very similar to how to the so the diffraction pattern that you have after a circular aperture, that essentially consists of eddy fringes, and those the diameter of the first spot, the radius of the first spot, is actually very closely connected to the waist size or the transverse extent of the Gaussian beam. That was one. And what we realized was that these Gaussian modes are actually called spherical Gaussian spherical mode, just because the phase distribution that we saw, of course, in the Z, the phase distribution is just like that of a plane wave, but in the transverse direction, the spread is almost identical to a spherical wave at points close to axis. Of course, remember, this is very important because we are finally dealing with paraxial beams. So paraxial beams means that the angle of divergence from the Z axis is not quite large. We are always going to consider basically just a very small transverse spread, and we are saying at the limit where theta is equal to tan theta and sine theta. So we have seen that in that limit it is very close to this is called a Gaussian spherical wave. And indeed, so the phase distribution is completely like a spherical wave. The intensity distribution, however, is like that of a Gaussian. But of course, on the z-axis, it is exactly a spherical wave. That is what we saw. Now, what we should just touch upon is that the energy flow across any transverse, any plane transverse to z, rather, to any plane transverse to z, or this is the propagation direction, right? So this is what we are going to study. And just we shall just start by writing down the form of the electric field, and that we saw was something like some ai, this is the amplitude, z0 by z, e to the I k z, e to the I k x squared plus y square divided by 2z, and e to the minus x square plus y square by omega square z, right? This is the complete expression that we got. You can see that the phase front is very close to in the transverse direction is like that of a spherical wave. This, and so then the intensity, of course, very clearly is given by, so there are these constants. So there is the c epsilon not by 2. This is the constant that you have. It is essentially this into the total intensity I, that is nothing but uh, in the transverse plane, in a transverse plane square, and that is clearly this phase part will disappear. So what you will have is a square. If I just write this in this way, it's 0 square. This is the actual equation, right? So we have assumed, so the actual equation is basically this is at large z, so you actually have a by 1 plus z square plus z0 square. So maybe it's fair that I write that down, no? I think it's fair that I write that down. I think it's not fair that I write this. Maybe I should just write this part. So essentially it is just this. Okay, I should write the complete expression. This is the actual expression, right? And this is was E. This is the actual expression, right? So then the total intensity is E minus, sorry. Yeah. Yeah, no, this is correct. 2x square plus y square by omega squared z, right? Okay. This is fine, right? So now this is the total, this is exactly what you have for a Gaussian. So what we have, what you can write is the rate at which energy flows. This is for vacuum, by the way. This is very crucial. So this is yeah, energy crosses any plane at constant z. So that will be nothing but integrating across x and y. So minus infinity to infinity and minus infinity to infinity, dx dy I of x y z, right? So that is very simple. So basically what I will have therefore is C. Acha, I missed this C epsilon naught here. C epsilon naught is there. Okay, so there is a C, this whole thing into, completely missed that, C epsilon naught by 2. So this will be C epsilon naught by 2 mod of a square minus infinity to infinity minus infinity to infinity e minus 2x square plus y square omega square z dx dy. Remember that my omega square z is actually omega 0 square 1 plus z square plus z0 square. So what I basically have, if I just write this e to the minus 2 x square plus y square, this omega square z, that is actually e to the minus 2 omega, sorry, 2 x square plus y square. This is omega 0 square 1 plus z square plus z0 square. Oh, here I forgot to write as usual. You guys are not seeing my mistakes. Okay, so this is what I write. Okay, so can you tell me what this will be, this function when I integrate minus infinity to minus infinity to minus this one? You can tell me the answer. Is 2.
Sir, it will be I guess pi by, as in both dx dy का integration ना.
Gamma function. These are basically gamma functions, right? So you will basically just take your,
Gaussian
you will,
functions.
yeah, right. So, huh?
Gaussian function, not gamma.
Sorry, yeah. No, but so you will,
So it will
yeah.
be
So essentially, if you
pi
just
by,
take root of 2w0 squared 1 plus z squared plus z0 squared, this thing you take as some t, and this will become dt. This t, and this one you take as some, this x part, x you take as t, and the other part you take as some s, and then essentially what you will get is some e to the minus t square dx dy, and this part will go out, right? Right. So if you take this as t and the other x part as y, you will basically get e to the minus t square dt and e to the minus s square dy minus infinity to infinity, and this part goes out, right?
so I didn't follow what you said. Like
No, so
basically you're
basically
saying
I'm,
we'll do substitution, right? Like just
yeah. You take
just
this as t and
yeah,
this as s, and then you
yeah.
derive, you take the derivative. This part is z part is constant, so that goes out,
Yeah, we can
right?
say
So
that
this
normally if
gets
you have a
cancelled out.
Gaussian which is e power minus alpha x square,
Hmm, hmm.
the integration of that is root pi by a, pi
Correct.
by alpha.
Absolutely. Absolutely.
So you can just
Pi
use
by
that
alpha.
fact. Alpha is that
Right. Right. Right.
2
Right.
by
Right. Right.
omega naught square
Yes,
1
that
plus
whole thing is,
alpha.
alpha. That
Huh,
whole
so
thing is alpha.
and you have two integrations dx and dy which can be done
Yes.
independently. So if
Independently. These are
you
completely independent
so
on
if
each
you
other, right?
multiply those two integrations, you'll get pi by
Yes.
alpha
Pi.
instead of root pi by.
Absolutely. Absolutely. Pi by
So
alpha. So this
so
part,
it, so
this
it'll
gets
be
cancelled off.
pi omega naught square 1 plus z
Yes.
square by z naught
Absolutely.
square by 2.
No, but and this part, but it'll cancel off this, no?
Yeah, that will cancel that
This
off.
outside. So basically, out the outside, you will get nothing but this pi omega naught squared by 4, right?
Yes, sir.
So is everybody following this? What we discussed. So basically, you just substitute this x squared plus. So these are independent. So just take 2x, 2. This whole thing is constant. This 2 omega. This part is constant. So you take that. This whole thing is like this. So you take the x part, and this essentially is, as Anirudh said, is alpha x square, alpha some alpha x square, alpha y square, and if you just substitute that, you will, the answer to that is root of pi y alpha, so that will just get out. I mean, yeah, I mean, you can basically just, it is very clear that if you take these as t, I mean, just do a substitution, then this part basically just gets out of the thing, and it cancels off the, it is root. So this is, you take each of them as, one of them as, each of them as root. So essentially you get just 1 plus z squared plus z0 square in the numerator, it cancels off, and the omega 0 square part leaves, remains, and what you get basically is this. So what is nice here, so what is your takeaway from this? So ixy is basically this. Is this clear to everybody?
Yes, sir.
Yeah, very good. So what is interesting, what is very something nice that we are getting, that is very consistent and all. Remember that this is at some constant z, but the transverse intensity at some constant z.
So
What?
it's not dependent on z.
Absolutely. That is the key dependency, the key takeaway, that is, this is not dependent on z, and that is something very important, because that is what we demand from the conservation of energy, right? Because otherwise, as the beam propagates and with z and it keeps on increasing, then something is deeply wrong, right? So very, this basically ascribes to the conservation of energy. Perfect. So this is not dependent on z. So before we, so this is great. So now this is, our basic understanding is done. But before we go into some other, the ABCD law, I think one thing we have to finish here, concentrate, just understand. Just keep on forgetting this. So that is the we have to spend some time on the this radius of curvature thing. So basically what we saw is, so okay, so we have your r equal to we have r is from the analysis that we did for q and r, this one, right? So very clearly this tells you that at z equal to 0, r is infinity. Very nice, right? So if I take my so r equal to infinity mane, you essentially have a plane wave, just something like that. There is no curvature at all. But this also tells you very clearly that when z, so this is my z equal to 0, right? As z is greater than 0, very clearly r is positive, and as z is less than 0, r is negative. Okay. So now the what we typically uh, sort of attribute to this positive and negative nature is basically what this means is, as you go from, so this is my increasing z, and of course z here is negative, right? This is z is minus, this
Sir,
is
I have a question.
minus z, huh? This is
So,
plus z. X second, Hitesh, just
intensity being independent of z, how does that imply conservation of energy? Because
because
intensity,
hmm.
unlike energy, like if it
Hey,
even
sorry,
if
sorry.
it
Hey,
is
this
not
is not
observed,
I. Hey, Hitesh, very sorry, yaar. You guys are not telling me. This is not I, right? This is energy. This is not I. Come on, this is I. E. Energy. Obviously, right? This is the expression for energy we calculated. This is the energy flowing per unit time, which is not dependent on Z. This is
yes, yes,
certainly not I. This is E. Intensity is, of course, this expression. No, where did I
yes.
write here? This is intensity. This is not. This is energy. Maybe I should write E. E is. I should
Or
not
maybe
write
write
E. No.
power or something.
Power. Unit area. Correct. I should, maybe pointing vector is a better thing. No. So this is like the pointing vector we calculated. No. I think it's better we write SXY or something, right? Because this is just the energy per flowing per unit area per unit time. That is basically the pointing vector, right?
So also it is not xy because we integrated over xy. S of z it is.
Absolutely right. Absolutely right. This is very right. Absolutely correct. Exactly. This is actually a subset. We integrated over x and y. Yeah, very good. So yeah, so this absolutely does not depend on energy. I mean, sorry, on Z. Very good. Yeah, perfect. Thank you, Andrew. So essentially, what it tells you is that, acha. So what do I denote as positive curvature? So let me again lay down some kind of a what should I say? I mean, this is a optics. May we typically use this as a convention that for an observer at infinity, if the observer basically sees a convex radius of curvature, then observer at infinity, if he sees, if they see a convex radius of curvature, they take it as positive. This is R positive. And if they see a concave radius of curvature, they perceive that as minus, as negative, as concave. They consider R as negative. So convex radius of curvature is R positive, and concave radius of curvature R negative. So here we are saying this again, this is, you can completely see that this is exactly what we had for concave, for our definition of mirrors. right? So we said that a concave mirror has a negative radius of curvature, and a convex mirror has a positive radius of curvature. Observer at plus infinity has a positive radius of curvature, which is exactly what we have here. So if this is very critical in just what we will do right now. That is in our ABCD matrix analysis for for Gaussian beams, how it sort of translates. Because there, you remember, a Gaussian beam we and understand as in in terms of the radius of curvature and the Q factor, R and Q, right? Those two. So R for the Q, it is basically just it is Q0 plus Z, so it's not a problem sign wise. But R is very crucial, right? Because it's a radius of curvature, and we know that in optics, at least for the mirrors, it was very crucial to define radius of curvature for concave and convex mirrors. So similarly, it is also important to define the radius of curvature for the Gaussian beam itself. And it's very clear that as you increase in Z, when you have a convex radius of curvature, we convey that to be this to be positive. And when you have a concave negative radius of curvature for the observer at in infinity, it is negative, which is something that is kind of consistent with our what we had, our convention for mirrors, for spherical mirrors. Okay, fine. So now we go to the next crucial thing, that the most important thing here, that is the ABCD matrices in the for Gaussian beam, ABCD law for Gaussian beams. For Gaussian beams. Very, very nice. Okay. So here, again, as you see, we basically have, in free space is very simple because here, the Gaussian just remains a Gaussian. What we saw is that as it propagates along Z, the waist expands. And nothing really is very surprising there, because you know that your Q is basically Q final. If we say that is like some Q initial plus Z, Q equal to Q0 plus Z. So Z is like a propagation distance, some d, and we know that it is just Qi plus d. So basically what we write here is, in free space, a Gaussian beam remains a Gaussian. It's absolutely fine. Remains a Gaussian. Gaussian as it propagates. So you have, very simply, you basically have Q equal to Q0 plus Z, and we typically write as Q final is some Q initial I, and this is, we say this is some distance, this thing d. So Z is basically d. Z is some distance propagated d. That is fine. And yeah, so basically you can also say that d is some, if there is if you have initially it was at Z final, it can be also be some ZF minus ZI or something. Final distance is ZI, initial distance was, I mean, final distance was ZF, initial distance was ZI. So if it went from a place, from D to D dash, so if it went from, if beam traveled from ZF, ZI to ZF, then your D is just some ZF minus, which is very trivial. This is not really interesting. What is interesting, however, is the thin length, and that is what we are going to look at now. This is a nice, here some interesting concepts are there. Let us just do the diagram. And again, I will use the advantage of electronic, having all these technology when we are teaching online. Actually, this is something which is really useful. I mean, in classroom classes, you cannot get nice figures like this at your command. This is certainly one positive of these things. And I, especially people like me who completely mess up trying to, make nice drawings, I think this is one hell of an advantage. Okay. Anyway, so basically, this is what is interesting. So you can directly see that one important thing is that if I am coming like this, sort of there is a beam which is basically coming from like this extent, coming like this. It goes here, and it sort of from here it basically uh, uh, so essentially what we are saying is that what happens to the lens, I mean what happens to the beam after it passes through the lens, is that it sort of the lens does essentially two things. It changes the focal spot size that we have obviously to look at, and it also changes the radius of curvature. I mean the radius of curvature it changes in the sense that it is kind of changing your concave whatever we had some the radius of curvature for the incident beam. It is basically getting somewhat changed for the because of the interaction with the lens actually. Okay, so what is, of course, there are two things which are important that we have to keep in mind. That is that immediately to the left and to the right of the lens, the spot size has to remain the same, because the lens is not, it does not change the transverse intensity distribution. However, the beam curvature is getting affected by the lens. Okay. So one important thing that we note here is that, so why, you can ask why this is so, ऐसा क्यों है. Okay, so for that the best answer to that would be to think that, again, see, we have what we have learned is that the Gaussian transverse phase distribution is very similar to that of a point source. Okay, I mean, sorry, to that of a spherical wave. What is the source of a spherical wave? The source of a spherical wave is a point source, right? So now think of this, that I have an object here, it's like a point source here, which is getting translated by the lens to the final point here, another point here. Okay, this is getting focused to here. So this will emanate spherical waves. So now think of this, if I emanate spherical waves like this to the left of the lens, then the curvature will look like this. Similarly, if I take this focal point and again consider the spherical waves propagating towards the lens coming, then they will be like this, right? So then, in terms of consistency, it is important to note that the change the lens will do to the curvature will basically be to convert this. And remember, this has positive curvature. Why? Because for the observer at infinity, this looks convex. So this is like positive curvature. The R is greater than 0. So here, similarly, it is negative because the observer at plus infinity will deem this to be a concave kind radius of curvature. This is a very tricky, this is the only interesting conceptual point here. The math is ridiculously simple. Okay, so so what am I trying to say? So for the transverse phase distribution of the Gaussian beam, Gaussian beam to the left and right of the thin lens. So this is, we are doing a thin lens. To the thin lens, consider the object and image uh, consider an height. Consider an object point source focused by the lens to an image point. Okay, so that means the radius of curvature of the object of the spherical wave emanating from, if I say that this is O, and this is I, from O has R greater than 0, R of C of the spherical wave from I as R less than 0. And it is also clear to you that if this is the object distance, then the radius of curvature at the surface of the lens, that is here, that is actually equal to the object distance, right? That is also very clear, right? So if I say that this is actually my DO and this is my DI, clearly DO equal to R1, and I should say Ri, and or maybe let us, yeah, whatever, you can keep it at R1 or R whatever it is, okay, keep it. This is R1, no? So I should keep it as Ri, R1, and Di is plus R2. Sign क्या
Sir,
होगा?
what is ZF and ZI? I mean, how
ZF
do you
has
define
Z's final and Z initial. So basically you think of a
final of
wave,
what? Okay.
so some wave here, it's like Zi, it has now gone to uh, ZF, and this distance is D. Okay, so just this Gaussian beam at here, it has traveled this D distance.
No, so like in this diagram here,
Here, no, here
yes,
there
sir.
is, I'm not showing anything. I have not come to ZF, Zi. Array, this is very different. This is in free space, completely different. Don't even think of Z. I have not even touched that, Hitesh. I have not considered any propagation. I am just thinking of the wavefront here. I mean, the Gaussian wave, the spherical wave part of the Gaussian in intensity profile, or the field profile, or at the input aperture of the lens, and this is the output aperture of the lens. I am
Yes,
not
sir, that is
considering
fine.
anything of that.
Okay.
Okay, okay, not ZF ZI. वो सब वो complicated है, right? Because then you need to know the ABCD law कि वो तो we have not even defined how the, at the moment we have not defined anything about the ABCD law at all, right? We are trying to figure that out. So,
Okay. I was thinking like
no,
in
no,
that
no, no, no.
sense.
That is, please, no, no, no. That is nothing to
Fine,
do
sir.
with that. That is
Okay.
nothing to do with that. Okay, so we are just at the thin lens part here. Okay, so basically what we are saying now, अच्छा, now what my question was, तो ये sign क्या होगा DO का sign, this one, this will be plus, right? Because this is here for the observer at infinity, this is plus. And remember that the DO DI are both positive, right? Right, because they are quite clearly their distances which are cannot be negative, right? So then very clearly, if this is plus, this has to be minus because R2 is negative, right? Is this part clear? Because here I have a concave wavefront with respect to the observer at infinity, which we define to be negative, which
Sir, I
means that
understood. Sir, I
huh,
understood why R is positive and negative,
hmm,
but why did you say D naught is positive
it's a
and DI is
distance,
minus?
right? It's
I
basically
mean,
a
the
distance.
magnitude of
So
the knot
magnitude,
and
yes,
the
that's what I'm
magnitude of
saying.
that thing should be the
Ha,
same.
yes, that is what I'm saying.
But I didn't
The
understand the sign
magnitude.
convention of the D part.
So basically, what we are trying to say is that since we are using these, why does this thing come again? Hide. So basically, what we are saying is that since we are sort of, I mean,
Oh,
so,
sir, I think I got
acha,
it.
no. So this is basically for the why you are saying this. So this is for the converging lens. You have this, na? This is clear, right? So both are positive. For your lens maker equation, say this is a convex lens. You know that these are both taken to be positive, right?
Yeah, I understood it,
And so
sir.
therefore this has to be minus R2. Is this clear? But this is an important point that Anirudh has raised. So because this is a converging lens, we know that the lens maker equation is this, right? Equation for convex lens is this, right? So both are positive. So then you have to have di as minus of R2. Okay, right? So now what is again very crucial is that the waist size, that is, if I take the waist size like something like this, immediately here as some wi, w1, sorry, and this one as something like w2, that also they by definition they have to be equal, right? W1 is equal to W2, because immediately after this thing the lens does not do anything. Of course here it's different, but W1 is, so we are going to derive this focal spot relationship. What happens? So suppose you keep the lens on a on a waist, and then you, what happens when you converge to the new waist, how they translate, we are going to derive that later on. Abhi kal, next day. Anyway, so very clearly these two are my main, this is one condition and these are other conditions. Okay, now let us just proceed, and this is my lens maker equation. So this basically implies now that 1 by R1 minus 1 by R2 is 1 by F, which implies that 1 by R2 is 1 by R1 minus 1 by F. Okay, now we also know that, let's go chota karna, now we also know that your 1 by Q, we have 1 by Q is 1 by R plus your I lambda by pi W square, right? And so that means now I will define a Q initial and a Q final. Qi and Qf is typically how we do. So basically this means that you have 1 by Qi equal to 1 by R1 plus I lambda by pi W1 square, right? And your 1 by Qf is 1 by R2 plus I lambda by pi W2 square. Okay. So that means that, and I know that your W1 is equal to W2 very clearly. So these terms are the same. This term and this term are the same. This term and this term are same, right? Lambda is of course the same. So basically what we have is 1 by Qf is 1 by R2 plus 1 by Qi minus 1 by R1, right? I'm just substituting here. I can just yeah, I mean, because these are same, so I can just write this. Yeah, this one is this, basically I'm putting iske jagah, I'm putting this. Is this clear? Instead of this one I'm taking this, and iske jagah I'm writing this. Okay, fine. Okay, acha, isko, shall we go to a new slide? Let us go to a new slide. Okay. Why does it not zoom out suddenly? I don't know. Anyway, so basically,
Sir,
continuing
why are
from
we
there,
going back to the definition of Q?
अरे because the Gaussian the ABCD matrix वैसा ही होगा ना. Remember the parameter for Gaussian beam is Q and QI and QF, right? That is the beam parameter. You have the beam, basic beam propagation is by Q parameter. That is what defines, tells you how the Gaussian beam basically proceeds. Right? That is how we have a Q final and a Q initial. That is the whole descriptor of the Gaussian beam. The radius of curvature is also there, but the main, let me just write this there. The main,
Sir, if you know RZ and WZ,
ah,
even
that is
then,
okay. That is okay. But then the RZ and WZ are the sort of the properties of the beam, but the Gaussian beam parameter is actually Q. I mean, that is the you can say that this is like a propagator for the Gaussian beam. Okay, the main parameter which, and remember why is that? Because for the, see, it is basically that parameter which has both information of R and Z, right? So what changes when a Gaussian beam propagates along Z? R changes and Z changes. So how do I map that? I map that using Q, main parameter which we track for Gaussian beam propagation is Q, right? Because Q has information of both RZ and WZ. So obviously you will keep track of Q in order to know how both have modified, right? So this is the reason that we keep all the Gaussian beam propagation and its interaction with different optical elements is mapped out by changes in Q, because Q has information of both the radius of curvature and the waist. ठीक है?
okay,
Clear?
sir.
Okay. So यहाँ पे हम क्या देखे थे? So basically again let me write. और ये यार वो step था, क्या step था? Okay, 1 by Q something, no? So 1 by, yeah, this one I think, right? 1 by QF, 1 by QI plus 1 by R2 minus 1 by this thing, right? Okay. 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 So now I have the lens maker's equation. उसमें क्या था? So basically we had this 1 by d0 plus 1 by di equal to 1 by f. So ये r1 minus r2 ये इसको बैठा दो. So this is basically that. R2y लिख दिया. Oh, really यार. R1. So you can straight see that this is from here. This is basically 1 by qi minus 1 by f, because this is basically 1 by r1 minus 1 by r2 is 1 by f. So this horrible, right? So this is fine. अभी हो गया. So that means क्या? तुम्हारा qf is 1 by, right, 1 by whole thing. तो इसको थोड़ा ठीक करो तो आएगा f qi by f minus qi. ठीक से लिखोगे तो आएगा qi by 1 minus qi by f. Now we know d for lens
Sir, your voice is lagging.
Sir, we can't hear you, sir.
Is he there or something? Okay, left.
Yes, left.
Will he come back or something?
Guys, can you hear me?
Yes, sir.
Yes, sir.
Baap re baap. This never happens actually. Suddenly,
Till
this
now, till now there is problem, sir.
there's problem. Huh?
Yeah, means there
Now
is
it's
a means yeah, lagging
lagging or something.
something.
Now it's fine.
There's lag. Let me see. Let me reconnect this Vodafone. Oh man, really? Oh, it's just in the middle of this. Never happens. Hello.
Yeah, sir.
Okay, it's still there. Okay, so I changed network and it hasn't thrown me out.
Yeah, now
So
now you're
hopefully it
audible
is better.
clearly.
It's better. Okay, so Vodafone is gone. Oh man, really, just in the middle of the whole thing, it is so horrible, no? Anyway, let us just, I was horrible, absolutely. Anyway, so let us come back to where we were. Oh, so so this is what we derived, right? So QF, basically we got as QI by this, and what we can basically write is this as QI by minus QI by F plus 1. Remember, this is my ABCD matrix for the lens, So basically the law is, and that I'll ask you, we are almost done today, so it's okay that it went. So the basic law is that the final Q is given by the initial Q by this plus D. Okay. So what I want you to verify, and I can give this as an assignment, but this is too simple, that so what we actually had, what we did here actually was that we just took this, we tracked the thing from we tracked the QF, that is from the beam pupil, from this we tracked it from here. We tracked it from here. Okay. But it's also same actually. This is very trivial. So basically, you see, we tracked it from here up to this point, right? This is what we said. This is what we said, right? This is what we said actually. So now, if you just think that this part that it propagated was some like D0 or something, then it is very simple to check, and you check this, that so you know that if I travel by D0 and then I focus this minus 1 by F1, what we actually get is something like 1 D0 minus 1 by F and minus D0 by F plus 1. I want you to check that you will actually get something very absolutely the same. You will get UI plus this will be D0 by minus QI by F. Oh, sorry, this is minus D by D0. Oh, minus D0 by F plus 1. It is very trivial. Just instead of QI, you put this, and it's, yeah, but check that. Can you check that? Can you check that tomorrow for the next class?
So what we need to check? Can you repeat?
Basically, what I did now was just the transformative action of a lens, which came to this, right? So from here, I am claiming that for the ABCD matrix, when you have for the lens, this is the ABCD matrix for a lens. The QF is the QI and the QF. So QI is transformed to QF by this formula, by this kind of a relationship. Okay. So I am saying that what easy way to check this is if you track propagation, that is by a distance of D0, then focusing, which will basically mean that the matrix is like this. So I'm saying that check that in this way that the QF will QI matlab the QI is here at this point. This is QI, and then it travels D0, then the lens focuses it to the new point, that is QF. So just show that this okay, no, wait, there's a difference. I'm not saying that it travels this much distance. I'm saying that it just goes from the lens finishes focusing. Okay. and it goes by the thin lens equation, just the focusing part. So show that after it travels d0 and the lens focuses, the qf is related to the input qi, that a qi mane at this point before it traversed d0, do or d0, that is related by this, which is basically going to again demonstrate that for ABCD matrix, for a Gaussian beam rather, the ABCD matrix transforms as this. QF is QIA plus B by QIC plus D.
Okay, sir.
Okay, just verify this. Very easy, very simple. Okay, it's quite from here itself, it's obvious, but just try that out. Okay, so next class we will just ensure that you have tried. I'm not putting this as an assignment, this is too easy. Next class we will prove that the focusing, we use the formula many times, for example, in your fiber thing also, that your WF is basically lambda F by pi W naught. This we are going to prove. This is something we are going to prove. This is the final waist size, and the initial waist size is F, and final, this I should put as I. Right. So this is an important thing which we learned, which we use so much in the fiber experiment, and which we can intuitively say, but we got to derive this using the ABCD law, and we are going to start the very important thing of how Gaussian resonators, how Gaussian beams interact with optical resonators. I mean, using the ABCD law, it's very interesting, and then I will also discuss a very important assignment problem that I'm going to give you, that is designing a ring cavity, which is very interesting. And Bishwajit can give testament to the fact that it took them some time to solve that. We'll just discuss it. Okay. Okay. So have a good Diwali. Hopefully crackers are banned where you are. It's not a safe time to burst crackers at all. So is COVID, I'm stopping to present. So what, COVID is reducing? You guys believe that COVID is out of India?
No, sir.
No, sir, there will be a second wave.
Oh, you guys are, I don't want to record all this, then people will, I don't know. Oh, Anubhav is going to you. Anubhav, are you there? So please.
And sir, it is still recording.